In the previous sets of slides, we developed the concept of shear flow, and we argued that shear flow could be used as a unifying concept for analyzing joints in built-up beams. Here I would like to further demonstrate this point by considering several types of built-up beams. So let us recall that the shear flow is defined as the shear force transmitted by the joints divided by the unit lengths or representative lengths, and the choice of these lengths you will see will be a bit problem specific, and that's where we will focus. But whatever is delta F and delta X, the shear flow is equal to VQ over IZ. So now what I would like to do, I would like to exercise this formula by considering area joints, line joints, and point joints. Let me start with the glue. That's the area joint. This is the free body diagram used previously to analyze the glue. And let me see how we can recover the result we obtained earlier by looking at the shear flow. So first, the force to be supported by the glue is equal to tau, the shear stress, times delta A. Of course, delta A, the elementary area, is equal to B delta X. Now, I say that the shear flow is delta F over delta X, which is simply tau B. Now I use the generic expression for the shear flow, which is given by this equation. And now I can combine these two equations to obtain tau as VQ over BIZ. Of course, we knew this result from the very beginning, but here I would like to go using the shear flow. Next becomes a little bit less expected. Let us consider two metal beams connected by two welds. The welds are shown here, and the other weld is this one. Since it's not visible, I show it with a dotted line. Now, the free body diagram relevant to analyzing these welds involves the two normal forces generated by stresses distributed over A star, and the welds produce forces Q. Q is the force per unit length in the weld. It's a relevant choice of forces because the welds are basically lines. Now, delta F, the force carried by the joints, is equal to 2 because I have two welds, and the force in each weld is Q times delta X. So with this in mind, I obtained that the shear flow carried by the joints is delta F over delta X is equal to 2Q. Now comes the generic expression for the shear flow. And now we can combine this equation and this equation to calculate that the shear flow in the welds is equal to 1/2 PQ over IZ. 1/2 is, of course, present because I have two welds. And it also tells us that the way the welds are classified or their strengths is classified is by recording the shear flow they need to support rather than the force or the stress. Finally, let me look at nails connecting two wooden beams, could be bolts, connecting metal, screws, whatever it is. The important point is this point joints. And now comes a very important choice along the x-axis. So instead of using delta x, I choose as the reference length the spacing between the nails, because that's what really tells me how nails are distributed along the beam, right, with a certain spacing s. Accordingly, my free body diagram will involve the familiar red forces, and the only force that I show is the force transmitted by the nail. I have only one nail in this setting, right? So there is only one force. And now let us see how it works. First, of course, delta F is equal to Fn. The shear flow is delta F delta X, but in this case, delta X is S, the spacing, and therefore the shear flow is equal to F sub n over S. Bring back the familiar equation, put together these two to obtain that the force in the nail is equal to VQ over IZ times S. So the larger is the spacing, the larger is the force carried by the nail. Accordingly, when we record the strengths of nails, we should record the maximum shear force the nails can sustain.